Too many people here today. So some of you mentioned that you're having trouble running jobs on CHPC. You should go back and take a look at the slides that Anita presented. It's there on the website. You have the option of specifying a different queue. So right now, if you're using the default job scripts, your queues are set to the class account, which is CS6965. So this will be in your job script, PBS-A CS6965. That specifies which account to charge. You have the option of specifying owner guest. She talked about this as well. Owner guest is nodes of the cluster which are owned by specific groups and might be idle, and many of them will be idle because they're not going to be used the same amount. The only risk there is that it can get terminated if they come and try to start the job before your job terminates. So it's actually good for debugging. Let's say you're debugging and you're not doing the final run. Go ahead and run it on owner guest because that might the turnaround time might be much lower. The other thing is that if you submit an owner guest, it's quite possible that overnight there's going to be a pretty big time window, maybe 2 o'clock in the morning to 4 in the morning or something, where it should be empty. So if you time it there, you should easily be able to get even your larger jobs through. Okay? Has anybody tried owner guest?
I use it for deep. When I want to run like 10 minutes, 5 minutes, it's much faster to get space on.
Okay. So I think you should all try using that because that's going to get you through. Make sure you submit your jobs because at the very least, make sure that you have your jobs submitted before the deadline. Okay? We've got it extended by a week. I still don't have your Hadoop cluster yet. I should hopefully get it later today. So your official Hadoop assignment is not going to start until next Monday. So you actually have the whole of this week till to finish your assignment. So make sure you finish that and get your jobs through. Has anybody been able to run the full jobs? Yeah. Okay, you got through, right? Yeah. I would usually expect, I don't think CHPC is that busy. Typically within 24 hours or a little more than that, you should be able to get it through. If you're still having trouble, say, getting your jobs to run by Friday, send me an email, okay? And we can take a look at that. Yes?
You leave your wall time at less than an hour, you leave those.
Yes, so that's a very good point because it also depends on how much time you're requesting. If you're requesting 24 hours of wall time or using 16 nodes, you're not going to get scheduled for quite some time. You need to make sure that you have a reasonably good estimate of how long it's going to take you to run your job. And you have to be as close to that as possible. And then you're going to get it allocated. Especially when it gets really long, it's going to be difficult, especially since there are so many of you and all of you are submitting similar jobs. Make sure that your wall time estimates are reasonable. You don't want it to be too tight because if there is any sort of resource contention, your runtime is going to go up and you don't want your job to get killed when it is 95% done. So give it a little bit of a room sort of to exceed your estimate, but give a good estimate. And was this for the full sort or?
This is a quick sort of 1 billion on one node, and for 45 minutes.
Okay.
I may have done something wrong.
45 minutes
Yeah.
for 1 billion?
So I don't know if my script is working.
Okay. Okay. It should definitely not take that long. If you want, I can run these cases and I can tell you how long it's supposed to take. In an ideal scenario, your case might be a little bit different, but at least I'll try and I'll post an announcement on how long I expect it to take. Okay?
So the 45 minutes is what I allocated, but it took much less.
Yeah, it should be to the order of a few minutes, right? So
But if I put more than like an hour, then it takes a while
Right. No. So as you are debugging, you'll get a good sense for it. And keep in mind also the fact that you're doing scalability. So if you're so think back about doing weak scalability. So you know what the grain size is going to be. So you know how much time it's going to take. And you can factor in like a factor of 2 or a factor of 3 when you go really large, that's going to be the overhead. But you should be able to predict it to some extent. So when you're submitting your smaller jobs, use that as a clue. Don't just randomly allocate, say, 5 hours and then wait. But at least, even if you do that for the small jobs, once it runs, it tells you how long it took. So make sure that you use that to estimate the time for your next job. And that's just going to help you turn it around quite a bit. Even if you're off by a factor of 2 or 3, it should still be, the actual runtime should be small enough. So half an hour is fine. I would probably by default put half an hour for most of, testing jobs, unless you have a wet thing. So half an hour is fine because at the lower end it's good enough. But if you're giving you're requesting a lot of wall time, then you have to be careful because that's going to take time.
Half an hour and how many notes? How many comments?
So I'll give you sort of rough estimates there. I'm just saying that if your estimate is for 5 or 6 minutes, let's say that's your estimate, how long you think it's going to take. Putting half an hour is fine. I'm just saying that you can floor it off to half an hour as the minimum amount of time, or even 10 minutes, it's fine. But for most of your sort operations, especially not counting I/O, that's why I said I'll give you numbers. Not counting I/O, they should be to the order of a few minutes to sort it, if you're doing it properly at scale. So maybe 15 minutes for the largest problem per node. And a good estimate here would also be how long does it take for you to sort using standard sort sequentially. And that sort of already gives you a rough estimate of what the time is. You're doing that twice. The total overhead of communication should be that much or less. So let's say that you say that I end up with 1 million keys of whatever sort type on each process. Run it on a single core and figure out what the time for just doing that sequential sort is. That already gives you an idea of where you should be. If that takes, let's say, 30 seconds, I need to do sequential sort on N over P keys twice. So that's 1 minute. My communication overhead should be what? Around that much. Let's say we give it a extra thing because your code is not perfect. 4 or 5 minutes. But if your estimate for the sequential part is 1 minute and you're allocating 10 hours, then something is wrong. So you can already do some simple back of the envelope calculations to get an idea of what sort of time you should expect, right? We are trying to write efficient parallel code. These algorithms are reasonably good for the scale at which we are testing. So use the sequential part as an estimate for what it is. And you can give it enough of a buffer. So you can say that I'm going to estimate that it's going to slow down by a factor of 5 or a factor of 10. But you will see that the actual time for the sequential sort is going to be so small that, again, allocating something like half an hour or something would not be a problem. You can extend this when you're considering I/O as well. This is how much data I need to read in on each process. This is how much time it takes. I'm going to read, I'm going to write. You can do a simple test on a single process and then scale it accordingly. You just need something which is approximately correct, and you put an extra constant there. You don't want it to be completely wrong, right? So make sure you do some of those kind of tests to figure out where you are. Okay?
Even if it's possible to access GitHub from Kingspeed.
Get what, sorry?
Can we access GitHub
You should
from
be able to.
Kingspeed?
You should be able to. So there is a problem with that.
Yes.
So the issue is that Kingspeak does not allow, I think, SSH authentication. So you should be able to access it if you use the HTTPS.
I have the HTTP also.
What? Has anybody done?
I tried it, I
You can use normal gate protocol instead of using, gate uses SSH, so.
No, so if you, as long as you, so if you go to your GitHub page and it gives you the address,
Right.
by default it's going to give you an SSH address. You can change that to HTTP. I think I don't know for sure, but I would expect it works. It works, right?
It works. You just need to authenticate using a user.
Yeah, exactly. You just enter your password. That's all. But it should work.
I'll double check.
Okay. And okay, so let's start. So we're going to talk about clustering today, and in many ways, clustering is sort of beyond the scope of this class. You know, Suresh is going to be teaching an entire course on clustering next semester. But I want to introduce you to it because it sort of ends up being a very essential part of data analysis, and we'll sort of be using it in some of the topics that we cover later on. So this is a very, very rushed introduction to clustering. And I'm simplifying certain things, I'm skipping certain things, but hopefully you get a decent enough idea, at least to understand and appreciate why it is a difficult problem and what sort of compromises we have to make when we want to cluster large amounts of data in parallel. Okay? So this is what we did last time on PageRank when we specifically did topic sensitive and link spam. Hopefully that part is clear to everybody. Let's think in terms of clustering. Now, conceptually, the idea or notion of clustering should be clear to all of you. When we specifically think from a slightly more mathematical sense, we need to sort of understand points. This is sort of a single sample that you are trying to cluster, and in this case we are trying to assume that they are somewhat homogeneous. So you could say that I want to cluster all animals and plants separately, and in the plants and the animals I'm going to have cows and sheep and everything. But in this case, the definition of a point is just going to change from being a goat or a sheep to being just an animal as a single entity, versus if you were clustering it based on the species, then the point, so to say, would be the name of the species. Okay? So the point is just that we have a large set, each of which is uniquely represented, and typically, in order to cluster, we need the notion of a space and a distance measure, and they are somewhat interrelated. A distance measure says that if I give you two instances or two objects, how far apart are they? Another way to look at it, if you think in the conventional sense, is how similar or dissimilar are they? So the distance sort of ends up being a measure of how dissimilar they are. The further apart they are, the more dissimilar, and the closer they are, the more similar they are. And so you want to have this definition. And in terms of it, mathematically, we define a space as well. So those of you who might have done vector analysis, real analysis, might know the general idea of a normed vector space. The most common case that you would think of are Euclidean spaces. The Euclidean spaces are spaces that you are used to. So think of measuring along a single line. So think of a one-dimensional line where we are defining distances just being the difference between the coordinates of two of these. Specifically, if you're considering Euclidean spaces, this is what we are normally used to, and it's generally the space of flat surfaces. So when you think of flat surfaces, like say this room, and we're measuring whether in 1D, 2D, or 3D, that's a Euclidean space. And you can, in general, extend that to n dimensions, wherein the notion of measure or the distance measure is clearly defined. The lines, the rotations, the angles are well preserved as we change it around. And more specifically here, this is like the formal definition of a normed vector space. But in terms of a distance measure, what is important, and this is also sort of overlapping with the definition of a normed vector space, is that it's non-negative. When we talk about distance between two objects, it is non-negative, and by definition it is symmetric. So if I'm x distance away from you, then you are x distance away from me. And probably one of the most important factors is that it respects the triangle inequality. And this is particularly important when we get to non-Euclidean spaces or curved spaces. When you're doing data analysis and we start thinking about complex definitions, things which are not points in the traditional sense, if you want to define the difference between, say, a cow and a goat, it's not clearly defined. You have to come up with a special metric which allows you to characterize this distance. This distance could be the number of teeth they have or the weight of the animal, right? So you have to come up with a metric. And so the distance, as you define it for these kind of special cases, has to respect the triangle inequality, which basically means that if I take 3 objects or 3 points and we consider the distance from A to B, B to C, the direct measure between A to C has to be less than or equal to going from A to B and then B to C, right? So think in terms of a standard triangle you might remember from your high school geometry classes. So that has to be respected, because otherwise it's difficult to cluster them. Because fundamentally what we're saying is that when we try to cluster something, we're saying that they are close together or they're similar if that distance is less, right? And you want to group them together. So these are concepts, and we'll sort of take a look at some of these. I can point you to readings on these topics further if you want. Now let's start with this notion, and at least for the first half of this lecture, let's limit ourselves to Euclidean spaces. So things that you can imagine. So think of, for the lack of a better example, just 2D points on the surface. So think of points on this whiteboard, right? And we want to cluster them together. When we are clustering, one way of thinking of it, and maybe in this case, I want you to go back to how we were sorting. You can potentially think of sorting as clustering data together, because we are defining an order and basically we're reducing the distance between adjacent elements, right? So in that sense, you can start off by thinking that there is a hierarchical or a divide and conquer sort of an approach. So think like merge sort, which means that we can start from every single point being a cluster of its own, and then we decide when to merge them together. So you start off with n points, and then you figure out which of these should go together, and then you can start grouping them together, okay? So those typically end up being hierarchical or agglomerative approaches, which are looking at all of them and are deciding how to generate bigger and bigger and fewer number of clusters with it. There are 2 other factors, the other one is point assignment. And as you can imagine, the first part, when you consider hierarchical approaches, because we are considering all of these points together, and we still have to figure out what is the best way to merge them together into a cluster, tend to be a little bit harder to parallelize. Because you're looking at each point, I need to consider it to every other point to figure out whom I should merge myself with. The other approach, which ends up being more commonly used, especially for large data sets, things that won't fit into memory, is to use a point assignment, which means that you're sort of bringing in a point sample, and figuring out whether it should be a new cluster or whether it should join or be part of a cluster that you have already decided. So one way of looking at it is that saying that, let me start taking one point at a time, create the number of clusters that I want, and then try to insert them. This is something like bucket sort. So think of the differences again. And both of them, as in the case of sort, have their own problems, okay? So in terms of connecting it to problems that you have experienced, I would say think of bucket sort for the second case and merge sort for the first case. The distance could be Euclidean, which means that I'm defining it something like the square root of the norm between the difference between the points. Or it could be something more complicated, like I said, when you're comparing a goat and a sheep, for example. Because this is closely tied up to the notion of a vector space out here, we have to think of whether we want to use the centroid of the cluster or not. So as we start grouping data together, we want a representation so that we can quickly test. If we were to take a new point in the point assignment approach, and we were to compare it to everybody already present there, then that becomes a n-square algorithm. And you don't want to do that. What you would do instead is to choose an approximate representation, which in the simplest Euclidean sense could be the centroid. So if you have points now, we can say that as I define my cluster, the cluster is defined by the centroid and maybe some radius. You can come up with your own definition of what defines this cluster. But when we talk about non-Euclidean spaces, the centroid might not make sense. More importantly, if you're analyzing, so the centroid, say in the first example, if you were grouping the animals together, is some hybrid between a cow and a sheep, which doesn't exist, which doesn't make sense. What you would do instead is to actually choose a particular sample, a single sample or maybe a set of samples, as representatives for that cluster and figure out, use them to define the distance as you're doing your further test. So it's particularly important when we consider non-Euclidean that the notion of a centroid might not make sense, and you might have to use samples just because averaging them, which would be the centroid, doesn't really make sense, and more importantly from a mathematical perspective, might not actually be in the same space. Okay? So that is something. The other consideration, of course, is that fundamentally from a clustering perspective, it's a computational challenge. We have n points and we need to do n square comparisons in an ideal sense to figure out who is how close to each other. But there might be an additional memory constraint as well, that the n points that we have will not fit in, which is basically going to decide whether you opt for the first or the second approach as we go about doing things. The final issue to consider is the dimensionality. If we are simply clustering points, Euclidean or otherwise, and they are low dimensional, say 2D or 3D, then the kind of algorithms that you opt for and the kind of issues that you end up with are very different from when we are dealing with high dimensional data sets. You might wonder what high dimensionality here means. Let's say that we want to cluster images. We sort of looked at this a while ago. One possible representation would be to take our 1 megapixel image, let's say it's, let's say it's 100, it's a 100 by 100 image. If we have a 100 by 100 image and we have basically, let's say it's a bitmap rather than a true image. So then we are talking of 100 by 100 bits representing this. And we can think of this now in somehow to sit in this high dimensional 100 by 100 dimensional space. That's the dimensionality. That's not just the physical, that's not like coordinate 100. It's not a although it's a two-dimensional image, that particular image sits in a 10,000 dimensional space. And that is the range at which we want to operate. Why does that affect clustering? It's basically a trade-off, and it's represented in many different ways mathematically, but a somewhat intuitive way to look at it is the density or the sparsity of the data points that you have versus the true dimensionality of the space. So let's say that we have 1 billion samples that we want to cluster together. If you take these billion samples in some fixed 1D or a 2D or a 3D space, we still have very, very dense data, which means that you're going to see another data set which is very close to you. If you take this and you switch over to a much, much higher dimensional space, then you're mostly going to be sparse, which means that approximations that you would use to measure the distance are actually not going to be bad. And typically in data analysis, you are going to be operating in the high dimensional sense, which means that as we compute things like the centroid or update it, we can actually use approximations because of the fact that the high dimensionality gives us this kind of a very sparse representation. It's not that you cannot have, it's just that if we were to have a very dense data representation in this high dimension, our problem sizes would be completely unmanageable. Because to get the same level of density for a high dimensional representation, you would really end up with a very, very large data sample. So we have other constraints there. From a computational perspective, so this is hierarchical clustering, and I sort of briefly defined as start with n clusters where you have 1 point assigned to each cluster. So these are all the points we want to cluster n points. And you have to define a stopping criteria. The stopping criteria might be the total number of clusters, or it might be the size of a cluster, or anything else. This is going to be very application dependent. So while we haven't really figured out, we haven't reached the stopping criteria, we're going to take 2 clusters, right? To figure out which 2 clusters to merge, and then we're going to merge these 2 together and iterate again. Picking 2 clusters to merge goes back to the distance definition. So we have 2 clusters, each represented by, say, the centroid in the Euclidean sense. And we want to merge the 2 clusters which are closest to each other, right? From a complexity perspective, each iteration out here, where we are trying to figure out which 2 clusters are the closest so that we can actually merge them, is order n squared, right? Is it clear why it's n squared? If I have n points and I want to figure out which is the pair of points which is closest to me, then I need to do that, right? Which sort of leads to an n-cube algorithm if you're doing it in a naive fashion. If you use something like centroids to update the value, you are reducing the size of the problem, so it's going to reduce to a n squared log n problem, right? In a sequential sense, we can actually somewhat avoid this by switching to an approximation. What you would do is that, and this is only true for, okay, I shouldn't say it's only true, it's generally easier for Euclidean cases, which means that instead of taking, when I'm comparing, figuring out which are the closest points, I can have cheat tests. Let's say, instead of doing the square root, I can say that if the x and y coordinates, or any of our coordinates, differ by a very large fraction, ignore it completely and do not incorporate it because I know it's far, right? More generally, you can use some sort of a binary space partition or an octree or a quadtree kind of an approach to already partition your data and then have a quick way of checking or figuring out which of the points are actually somewhat close, even if you don't know exactly. And then you can threshold them. So it changes from an n squared to an nk kind of an algorithm where you're only comparing or doing the distance computations for a small set of points. Okay? When we consider non-Euclidean spaces, I sort of briefly mentioned this, we need to first of all define what the distance measure is. How do you compare cows and goats? You need to define what the distance is. The centroid is not appropriate, so we need to choose either a single sample or a set of samples to represent the clusters that we have formed. In general, you can define a hyperplane partition, right? This is sort of would be the general extension of a binary space partition where you're defining a hyperplane. The example could be that you choose one particular sample, say you choose one particular cow, and say that this defines whether you are a cow or you're not a cow. So you can define these kind of similarities based on this, and the representation, the sample that you choose is going to be the hyperplane. And so you can start dividing up your structure, your set of points to figure out what it should be. The most popular, or at least one of the most popular clustering algorithms is a k-means algorithm. The disadvantage from the sense is that it expects that you know a priori what the number of clusters are in the data set, which is not always going to be true. So that's why it's called k-means, in the sense that you specify how many clusters you want to form from your data set. It's a point assignment algorithm. It assumes and Euclidean space, although you can have variations to account for non-Euclidean. And as I mentioned, the number of clusters is unknown. So the general way the algorithm works is that you choose k points that are likely to be in different clusters, and we'll get to how you might have an initial guess. But basically, you start off with k clusters, ideally thing, and for each of the remaining points, we're going to compute the distance to each of these k candidates that we have, and basically assign it to the one where it is closest. Update the centroid of this cluster, because adding a point or a sample to this particular cluster is going to change its centroid. And then you basically keep adding all the points. In order to make this a little bit more accurate, at the end of this, you can update those, use those as the new guesses, and keep recursing till you have converged onto a good enough solution. Is this clear? It's a very simple algorithm and fairly effective as well. But this sort of brings in the notion of why you need the distance measure, because I need to figure out which is the closest. And because I don't want to do the n-square computation at each time, I need some representation for each cluster, which in this case is the centroid. Okay? Is this clear? Okay. So how do you actually initialize the clusters? And at this point, I want you to sort of think more from a parallel perspective, both from a scalability issue as well as a memory issue. So one option is to actually pick what would be good candidates for cluster centers. Would be to try to pick points that are as far apart from each other as possible, right? So there are sort of two options here. The first is that you start off by picking up a random point, any random point. Now I want to compute the point which is furthest from this to be the next point that I'm going to add. So this is going to be an n-square computation. Sorry, this is an order n computation because I'm computing the distance from this particular point to every other point. And that way I can figure out another point. So basically, it's again a PSP kind of an approach. It's the dual of that actually, because you're not partitioning all the points, you're just simply computing the other points. So this way, in Kn, you can compute the k points which are somehow largest. Keep in mind these are approximation algorithms because it's very sensitive to the first point you pick. So if you do a bad job of picking the first point, you could end up with fairly weird partitionings and clusterings as a result. The other approach, especially if you know that your data is well distributed, would be to actually take a random sample of this data and then opt for a hierarchical clustering, which is going to give us a good initial guess as well, right? So keep in mind that one of the key reasons why we want to use point assignment instead of hierarchical is that hierarchical clustering is not going to work very well for large data sets. So in this case, we can avoid that if we know that our data is well distributed, generate a small sample, use hierarchical clustering because it's going to give you good results, especially if the sampling is efficient, and then use that as an initial guess for your k-means clustering. Okay? I'm going to present one particular algorithm which works very well. It's a paper by these three authors. I'll put the paper online, which works very well for high dimensional Euclidean spaces. Okay? The general idea is going to be the same, but there are some specifics which are interesting. They make one very strong assumption about the data, that even though you're talking of a high dimensional Euclidean space, they assume that the clusters are normally distributed along each dimension, and they are also independent. So you have a Gaussian distribution with different mean and different variance, but there's no cross terms out there. And I'll bring this back why that assumption is important or how it affects the rest of the clustering. So you choose k centroids as in k-means, and you start reading data in chunks. Okay? For the cluster representations, they are keeping three different kinds of information in memory. One is the discard set. This has two d plus 1 values. I'll tell you what actually I have it here. So the 2d plus 1 is the number of points, the sum, and the sum of squares along each dimension. Okay? The plus 1 is for the number of points, and for the sum and sum of square, they keep each dimension independently, and they keep the values along each of those dimensions separately. There is a compressed set, which is also the same, and then there is the retained set. We'll look at what each of these sets are. The retained sets are sort of the clusters that you are confident are clusters at this point. The compressed set is, and for the retained set, you're only keeping these values. Sorry, the other. For the discard and the compressed set, you're only retaining these, you're not retaining the actual points. For the retained set, you are actually keeping the points in memory. So you're bringing in points one by one, and you want to know what to do with this. The three options are either to keep this point for later calculations because I don't know which cluster it belongs to. I can add it to one of my clusters and then get rid of the point because I'm confident that it definitely belongs to one particular cluster. Or I can keep it in a sort of a smaller cluster which does not yet map to my main K clusters that I have started off with. Okay? In this case, that would be your definition, that those which didn't get assigned to any of the main clusters. I've looked at all the points, and these are points which are not statistically similar to the points that I have seen or the clusters that I have created. So there is a high probability that they are outliers. This is going to depend on the specific example application that you are deciding and what your definition of membership to a cluster is. So you're processing it on the fly one by one, and then you are saying that this is how these points which are not close enough to any of my clusters must be outliers. Okay?
The performance will change if I change the distance, like instead of Mahalanobis, if I use Euclidean or some Manhattan.
Mahalanobis distance, this is, okay, maybe I shouldn't, this is not the same as your standard. In this case, this is a Euclidean distance measure. The Mahalanobis distance is measuring the membership. So instead of saying that I'm going, so consider that I have a cluster here, right? I can take this cluster and say that I'm going to add another point if it is within a specific distance, right? So here we want to do something a little bit better than that because we are adding points one at a time, and I can get corrupted in the k-means structure if there are very few points and I'm only assigning myself to the closest point that's far. That is not going to work. Instead, what you're going to do is that you're going to use the Mahalanobis distance as a measure of this. This basically says that you assume the normal distribution. Then basically what you're saying is that, so if you say that there is a Gaussian distribution, right? So let's say this is one cluster. Now if a point comes along which is out here, do you want to add it to this or you don't want to add it to it? You don't want to add it to it because it is statistically very improbable that this point belongs to this cluster. If you simply did it on the distance and this was the closest centroid that you had at that point, you will assign to it and you will adjust the distribution to reflect that. But you don't want to do that because you have a stronger notion about what the distribution should look like. So Mahalanobis distance measures the variance, basically how far is it from the distribution that you have specified, rather than just the distance. The distance is the same, it's still a Euclidean distance. This is measuring the distance to the distribution.
I think the probability would be the right word.
In this case, yes, because the further you get away from it, the probability goes down. So you want to make sure that this is close enough, and you have to specify a threshold. Maybe you specify something like, is it like 3 sigma on either side or something?
You see, it's mathematical equation for the.
That's the one. So it's basically mu minus whatever x transpose S inverse. This is the cross correlation term, and in this case, so if you take this, right, there are no cross terms. it's going to end up like something like mu minus x transpose mu minus x, which is basically mu square minus x square divided by sigma square. Because this is not a matrix anymore, it's just a diagonal term, right? So, and this is only coming because they have assumed that the dimensions are independent of each other in the high dimensional space, which is not, yes?
When we say distance from the cluster, is it the distance of a point from the center of cluster or all points of cluster?
In this case, it's from the distribution that you have assumed for the cluster. So in some sense, you're doing it in a statistical sense. You have assumed a distribution, and so there are two choices, right? I can do it to the centroid as we described earlier, which means that I'm representing the whole cluster by just one point. That would be approach number one. Approach number two would be that I don't believe that this point captures all the information, so I want to compare with every single point, right? But that is computationally expensive. The third approach, what these guys do, is to say that as we build up, as we keep adding points to a cluster, we're going to have a statistical representation of the distribution of these points, which in the simplest sense would be just the mean and the variance, okay? And so that allows me to compare against all the points in some sense, in a statistical sense, in a cheap fashion, without having to actually go ahead and compare. It's independent of the total number of points that might be in a cluster. So that's the difference here. Clear? And is that fine? Yes.
I wonder how do we initialize the centroid of the cluster? And
So
then there-
this is going to be the same issue that you're going to have with all of these problems, because, and it's not an easy problem, because fundamentally you have this issue of the fact that data might vary over the entire space. So the typical approach is going to be to take a small set of samples and initialize it, or say that I'm going to do two passes. I'm going to start off with one random point, figure something which is sufficient, is the furthest away, and then basically pick k centers initially. Because it is a bit of a chicken and egg problem. You want this. If I knew these correctly, then the job of clustering is trivial, because I would just go and do point assignment at that point. So in all of these algorithms, the initialization is going to be. This approach is a little bit there because this k doesn't have to, you don't have to necessarily know k accurately. You can choose a large enough k, because we do maintain these extra sets, the compressed set and the retained set, which allows us to either start off with a smaller k and increase it, or start off with a large k and decrease it. So you have that flexibility beyond the traditional k-means, where you can somewhat at least accommodate. But none of these are foolproof, so it is still sensitive to the initial k centroids that you do actually choose. Okay. The other approach, which is actually quite interesting, and I'm giving you a very quick overview of this, is clustering using representative. It does assume a Euclidean space, but it does not make any assumptions on the shape of the clusters or the distribution. So it doesn't use, there's no assumption on, that it's a normal distribution, for example. A good example would be to say that you have clusters of this form, a blob in the middle and a ring outside, and you really want to get these as two separate clusters. The way it avoids this is that the centroid definition is not going to work in this example, because both of them are going to have the same centroid, right? If I took a mean out here. What it does instead is to actually use a collection of representative points out here, which are going to represent. So it's a subset, it's a sampling of your points, which represents this particular cluster. And membership and the process of merging clusters is all decided based on that. As with all the other approaches, you sample and create initial clusters by doing the hierarchical clustering. Once you have this initial guess for all the clusters, you're going to choose some samples which represent this cluster. And you want those to be well spread across the entire cluster to make it possible. what you then do is that you are going to effectively have a relaxation term. So you're going to move, and that's where the definition of the Euclidean space is important in this case, because this is not possible for the non-Euclidean cases. You're going to take these points. So in this particular example, you're going to move each of them towards the origin, towards the centroid, by a small fraction. And then you're going to see whether they get, any of these two clusters get close enough. And if they do get close enough, you're going to merge. And the intuitive way of looking at that is that assume this particular scenario and assume that this second ring out here is broader and broader and broader. You want to figure out at what stage should these two end up being a single cluster or not. And what this algorithm allows you to do is to actually determine a condition for the merging of these two cases. The rest of the approach is very similar to the previous one we talked about. You're just going to have an additional test by doing this relaxation to figure out if they are close enough to be merged. So now let's sort of look a little bit into clustering non-Euclidean spaces, and it's a slightly, things get a little bit more tricky. The algorithm that I'm going to describe here can be applied for Euclidean as well, because all it's interested in is a distance measure being defined. Yes?
So in the previous slide, in the retain set, are we considering all the points as outliers and we are discarding them?
No, you're not. So this is going to depend on the case. So the retained set is just going to be a subset as you're processing your points. It's a subset which so far it does not statistically map onto any of the clusters that I have. Once you're finally done with everything, so let's say that you start getting points into a retained set, and if many of them start getting close enough, you're going to create a new mini cluster. At the end, when I'm done with everything and I have only my main clusters, my mini clusters, and some retained points left, you can decide on two approaches. One would be to discard them and say that these are outliers, or you can relax your criteria that you use to test memberships, whether it's a distance or the Mahalanobis distance. You can figure out, you can just relax that condition, say that I still want to assign them to some cluster. This is the closest. I'm going to assign these to those particular clusters. Now this is going to depend very heavily on how you intend to use the results of the cluster. Is it clear?
So, if I'm not wrong, there might be 2 points that comes to the retain set. One are the points which are equidistant, or let's say, or the distance.
Well, in this, it's not necessarily, it's not only limited to distance, because here we have changed the definition of membership to these. So yes, you could have something which is equally distant, right?
And the other one is which is far from everyone.
Which is far from everyone, yes. And you can have your own strategies at that point to figure out, yes, you can have a strategy that some of these points in the retained set are uniquely identified as outliers and discarded, and the other ones are merged with the existing cluster. And these are sort of messy topics. Outlier detection is a very hard problem. And that's why instead of suggesting a specific way of dealing with these, I'm skipping this. Because, like I said, this is not the scope of this class. And that's going to depend very heavily on the application and, more importantly, how you plan to use this. And if the data, typically in big data type of problems, if you have sufficient amount of data, the clusters that you're formed, assuming that you're interested in the clusters themselves rather than the membership of a particular data point to a cluster, that the clusters that you're going to end up with are probably good enough if you have seen enough data at that point. In which case, you can just discard it and just continue with the main clusters that you have formed. If you are interested in specific membership, then the choice becomes a little bit trickier in terms of then figuring out some heuristic to assign the correct membership for that particular data point. Okay. So it's going to really depend on this case. If you focus on the first part, which is I think what we should do, then you have identified the correct clustering, even though some of these are outliers. So when you're considering this, typically you end up using a combination of hierarchical and point assignment techniques. this is similar to what we just discussed in the sense that you have no choice here but to represent clusters by sample points, and you keep that in memory. One specific idea which actually is sort of important for these cases, just that they scale well, is that you organize these clusters hierarchically in a tree so that you can do somewhat quick searches out here, because the standard approaches that we would use to filter out points are no longer going to work because of the non-Euclidean nature of it. And as we consider inserting new points into a particular cluster, you will traverse the graph, the tree, to figure out which particular cluster to insert this in. Okay? We look specifically at how the tree is set up and how we're going to maintain it. So this is a specific paper, but there are a lot of variations on the same kind of an approach. The clusters themselves are going to be represented by a set of features, and this is generic to a lot of non-Euclidean type of problems. So we need to define how we are going to represent this, right? So we're going to represent each cluster by, first of all, n, the number of points that are there in the cluster. The clusteroid is a point in the cluster that has the minimum cumulative square distance to all other points. So we're going to say that here, this guy, that is in some sense at the center of it, but the center here is defined not as the average, but the cumulative square distance to every other point. So this is again a n calculation that you have to do. We save that particular distance as well. I'm just going to refer to that as CST from now onwards, right? So you're comparing the square distance to every other point and summing it up, and that I want to store as well. In addition, you want to store two other set of points. So you've stored the clusteroid out here, and you want to store the k nearest and the k furthest points in this cluster. Okay? And intuitively you can think of it from the fact that as I add new points, the clusteroid itself might change, right? So if I'm adding new points, the point which minimizes the square distance to everybody else might change, right? At the same time, so the first part, which is the k closest points, are needed to update my clusteroid, right? The center of the cluster, so to say. The second part is that, why do I need the furthest points? That's because at some point, if I have to merge two clusters, then that is going to be decided by the points which are at the edges of our cluster itself. So think of this as a simple representation for the distribution out here. Because this is non-Euclidean, I cannot define mathematicals. I'm doing this purely by sampling. I have the centroid or the clusteroid. I have a set of points close enough to that, and I have points which are at the periphery of my cluster. Is it clear? And of course, k is going to now again depend on the specific application, but you have a flexibility in terms of it, and you've limited the amount of memory that you need to keep for representing a given cluster. Okay? Is this clear? So, n, the specific point, this is going to depend on whatever the type is. This is just going to be some floating point, assuming you have a correct distance measure. And then the same for the k, 2k closest points, right? So total.
So when you say non-Euclidean, how do you actually calculate? What would be an example of calculation of the closest point?
So the moment we get into a non-Euclidean distance space, right? The user, you have defined what the distance is. So you will have a function which is going to compute the distance between
Between any 2 points.
any 2 points. And so the closest is an extension of that, basically. That's all, right? So you have to define this. And try to understand why this is sort of important. So when we typically think of non-Euclidean, you're thinking of curved surfaces, right? Surfaces which are not there. So a simple example that you should consider here would be the Earth, for example, right? If you're measuring distances on the surface of the Earth, and you use 3D coordinates for this, and you want to cluster them together, you're going to get clusters somewhere in the middle of the Earth, let's say, right? If you want to cluster big cities and villages, you're going to get weird things which are not really there. The distance, as you should defined correctly, should be a geodesic distance. It should be on the surface of the Earth rather than a true three-dimensional distribution. So it's 3D, but the distance metric is really a 2D-ish measure. And so you need to define this, and this is going to be very specific to this thing. If you want to define image similarity, for example, if you're comparing images, maybe L2 distance is fine there. But that's something which is not immediately clear, and the user needs to specify that given two instances of this particular object, what is the definition of the distance between these two? And that you're going to use in a black box type sense, and all of these definitions, all of these assumptions that we make extends directly from that. And we have not made any other distribution about assumption about the distribution or how they relate to each other.
So, and when you say cumulative square distance, how would I calculate that? I would take any 2 points.
You take any two points. So it's, let's say that I want to measure the cumulative square distance from me to everybody else. So this distance square it plus this distance square and so on. It's a sum of square to everything. Okay? You can have variations on this if you want. You can go for it. So this is like they're keeping the square just because you're minimizing the total amount of work. You can go for an L1 type of definition as well if you want. You don't want, there's no negative distance here, so you don't want to bring that in. Okay? Clear? So like I said, the key factor to notice is that why we need the closest and the furthest points. Okay? And depending on the variability in your data, the size of K is going to increase. Try to think of why this is important. Because we are going to be doing it in a data assimilation fashion, I need to keep K because as I keep adding points, my centroid is going to move. So if the distribution, even though I don't know it, of the data is going to vary over time as I bring in new data, then I have to be more careful about having a larger set of closest points. And we will be updating this, so but let's look at the approach at least, and you're going to see different papers where they're going to cover different topics. I'm not giving you all of these, like I said, because that's not the focus, but in general, what you're going to do is that you're going to initialize this, you're going to choose a large enough sample of points.
Sample and then create this.
So you take samples, you create by hierarchy, you're going to build. So when you do a hierarchical clustering, you are going to get a kind of a tree anyway, right?
Yeah.
But because of the way in which we plan to use these eventually, you will not actually choose all the leaf nodes that you would have got.
Okay.
Because you might have some outliers ending up from your, or some very small clusters ending up from a hierarchical clustering of your sample data. So you will initialize, because the system allows you to create new clusters within the tree itself if possible. So you can split them there or merge them. So we will start off by choosing clusters which are of sufficient size in this thing. So you start off in a more conservative fashion. So you say that let me start off with fewer clusters, and then my hierarchy is built up if they shared basically a parent. And then you would set up your tree, and that's your tree that you're starting off with before you start off adding your points. Okay? Now, we're going to start reading points from disk or wherever else you have it, and we're going to traverse down the tree using the distance to the clusteroid. These are the samples that we have. So as you grow, start from the root, compare it to the samples out there, go down and down and down till you get closest to the leaf node. Now, once we reach one of these leaf nodes, this is just a way to quickly do it and avoid n search and then limit it to log n in the number of clusters. Once we reach the leaf, there's a bunch of things that we need to do. We need to increment n because we are adding a point to this particular cluster. We want to update the cumulative square distance for all the 2k plus 1 points that we have. This is the k nearest, k furthest, and the centroid that we have already, the clusteroid, right? This is easy because you're just adding the distance of the new point, p, let's say, to all these 2k plus 1 points. So this is easy. It's a fixed cost of 2k plus 1 as we update their distances. Is this clear? Right? You're adding the square distance to the new point to each of those entries. we also want to estimate the cumulative square distance for the new point, right? So we don't know what it is, and we have discarded all the earlier points, so it doesn't make sense for me to recompute it, right? We're doing this we are adding points, right? So I don't have the earlier points, I only have the cluster, I don't have the points themselves. So you approximate this, and this is true for high dimensional spaces. This is a somewhat of an approximation for lower dimensional spaces, but basically you do the cumulative square distance for the centroid, right? What does that mean? So think of how it is. Let's say that you are the centroid for this cluster and I'm the new point. What I need to do is to figure out what the distance from me to everybody else is. Instead, I'm going to represent this as a combination of two terms. The distance from me to the centroid and the centroid to everybody else. Okay? Think of it loosely as a Pythagoras theorem kind of a version. In high dimensional space it holds. So this is the distance from the centroid to all the points so far, and this is the additional term from me to each of those points that I have as a result of the centroid.
But you have to also update the centroid.
Which centroid?
As okay,
No, we updated that distance. There are two additional steps here. Just hold on a minute. This is just an approximation, right? The other way to look at it is that if you think of updating the mean and the variance on the fly, we're only doing the first order approximation here for this distance. Yes?
And then give the part like why are we updating the CSDO for the 2K plus points?
Which one? This one?
This one, yeah, this one. I did not, yeah.
So I've added a new point, right?
Right.
So the CSD has changed for these points.
Okay.
So
this centroid has changed.
Centroid might have changed, we don't know.
Okay.
But the centroids, whatever, so let's say you were the centroid and those are all the other points, right?
Right.
So let's say there are 10 points right now. So your CSD is the sum of square of your distance to everybody else.
Yeah.
Now, if I am being introduced into this cluster, then your cumulative sum should also factor me, right? So that's the new point. So that has to be updated, and that has to be updated for everybody else that you've kept so far, right? So we have to update those 2k plus 1 points which represent our clusters. The k nearest, the k furthest, and the centroid, clusteroid have to be updated with this extra term now, right? The second part is what is actually an estimate for me, the new point, the cumulative distance from me to everybody else, right? And that is what we are representing by the combination of basically the distance from C to those points and the distance between this point and the centroid, right? Is it clear?
Yeah.
So, and it's scaled by a factor of n because I have to do it for each of these. So you can think of expanding these guys out, right? So this would be sort of the distance from C to P1, C to P2, C to P3, and so on. And I've taken those, and each of these n terms is now going to add, and that is an approximation by my triangle inequality effectively, right? Is it clear? Okay. Okay. So let's say that, where is it? Okay, let's go. Okay. I want you to consider clustering in a streaming model, okay? And it's easy to imagine, think that, data is flowing in, so there is a time aspect right now. There is more recent data coming in. Maybe it's a Twitter stream that you're thinking of. And we are interested in considering queries or clustering where I have access to a window of size n. So I have some access to data, and maybe there are queries. Maybe this n is 1 year long, and you might be interested in what are the most common topics in the last week, in the last 5 days, in the last 7 days. And you might have different queries of this sort, but you would like to answer all of that in one go, right? So Twitter would like to say build a model, and then you log on to the system and you say that I'm interested in what are the most important clusters or which are the k most clusters in the last 1 week or some arbitrary period of time, up to whatever n they have chosen, right? So that's what it is, that we are assuming that there is some sliding window of n points, data points of whatever sort, and we are interested in clusteroids of the best clusters formed within the most recent n points. This is the history, the time window, and we would like to answer this together. And basically the idea is that you want to pre-cluster it in a way so that the queries can be answered quickly, right? So you're not dealing with all the data, you're just dealing with these guys. So the general idea is to, as data is coming in, you want to partition and you want to summarize it into buckets. Okay? Now the buckets are kind of similar to leaves of the tree that we had earlier, but they're serving a different purpose out here. You want to effectively store more information for things which are close by, and as we go back in time, we want to have larger and larger buckets. Okay? The important thing, and this is needed for theoretical proofs, but the general idea will be clear to you, is that bucket sizes are some powers of 2 by some factor. So, and this is because of how we are merging. This is going to, for those of you who might have played this game called 2048, it's going to look like a 1D version of that. So bucket sizes are going to be some constant times factor of 2, which means that they're going to be twice as large as each other. Of a given size, you can only have at most 2 buckets. So if you have a bucket of size 10, you can only have 2 of them. If a third one comes, I'm going to force it to merge and make a bucket of size 20. Okay? That's what I'm saying. You keep merging it, but then they are restrained to be non-decreasing as we go back in time. So what that means is that, let's go back to drawing here. So if we have, so you initialize buckets, we choose some p, and this is going to depend on exactly what kind of queries you're interested in. And that's the smallest bucket size that we have. For every p data points that we get, we're going to create a new bucket and timestamp the bucket based on the last point that we added. Okay? So data is coming in. The moment you get p, you create a new bucket. That's the smallest size that I've assumed. Okay? Internally, you have whatever strategy you want. You can cluster them together, right? So I take p points, I create a bucket, and I've clustered it internally. Maybe using hierarchical, or if it is even that is too big, then we opt for one of the other approaches. Additionally, because we are not interested in anything older than n, we can drop any buckets which are older than, which have a timestamp greater than n. At any time that we have 3 buckets of a given size, we will merge the 2 oldest buckets. Okay? So we had this chain of buckets. We have the timestamp so we know where the points are, and then we're just going to merge them. Keep in mind that as we merge these 2, that's why I said think of your 2048 game, this might have to propagate. So you add 2 p's, you create a 2p bucket. You might have already 2 2p buckets, you have to merge it and create a 4p and so on. So this is going to completely propagate back in time. Once we think in terms of, the key question is going to be, how are we going to actually merge these 2 buckets together, right? So the size of the new bucket is going to be twice as large as whatever we created. The timestamp of the new bucket is going to be the newer of the 2 smaller buckets that we are merging. And we need to decide on whether we want to merge the clusters or whether we're going to retain the individual clusters which existed in these 2 cases, right? And this is going to depend on the kind of data that you are merging. So I'm going to give you examples from a Euclidean case where we are considering k-means, and the non-Euclidean case if you were doing it. So if we are representing, we're sort of considering a Euclidean case with k-means, and let's say that we are representing each cluster with the total number of points in the centroid, then you would basically, this is fine, to merge, your update would be to just update the number of points in the bucket, in the merged bucket, as well as to update the centroid. Right? That's all that you need to do, and you can move on. So you have a time history of what each of your buckets contains. If you consider the non-Euclidean case that we talked about, it becomes a little bit trickier because we are representing the clusters using a clusteroid and the cumulative square distance. Once we merge two clusters, we need to think of what the new clusteroid is going to be. And the new clusteroid in this case, if you think of two clusters now, is actually, where do you think is going to come from?
In the lowest case and the largest case, right?
It's going to come from one of the points which are furthest from each of the clusteroids,
Yeah.
because that's where you're going to be merging these two, right? So it'll be one of the k points furthest from the clusteroid, and you can now, using the same argument as I defined earlier, you can define it in terms of computing the new clusteroid center. So you want to compute for each of those k furthest points, what would its CSD be for the merged case? And that can be written in terms of the CSD in the first cluster, which you already have, the number of points in the second cluster, and the distance of moving from this point to the center of the first, moving from the center of the first to the center of the second, and then the CSD of the second point. So in the first case, we move to the center and to each of the points. Now we are going from these points to the first center, second center, and then back to the points. And that gives us an update for what the updated CSD for any of these points is. So it's similar to what we did, but now you would have the updated values out here. Compute the new centroid. You will have 4k nearest furthest points. You want to use that set to figure out what the new k closest and the k furthest points are. You have updated and you can move on. Is it clear? So depending on whatever representation you chose, you would have to update these guys and move on. Finally, if you have this kind of a representation in a historic sense, where you have, clusters which are of, in ever increasing bucket sizes, then what you would do is to choose the number of buckets which are at least as large as m. Given the binary nature of this, we cannot precisely guarantee that we have the clusters that we have formed correspond to m, but you can give a limit that it's between m and 2n points because of the nature of that. And so this is going to be the most efficient way if you want in a single pass to get somewhat arbitrary. And this makes sense in the sense that most of the queries are going to be sort of geometric in time in terms of the kind of query. So you're not going to say that, I'm going to say 1 week, 1 month, 6 months, whatever, rather than saying that I need, 57 days from now or something, right? So for those kind of use case scenarios, this gives you a way of generating the right clusters at different time scales. And like I said, the merge part was the sort of the